Basic routing and IP utilities. Up until this point, we've talked about layer 1, layer 2, we've talked about IP addressing in layer 3. Now we're actually talking about devices that are in layer 3 routers and what they do. So to start off with routing, know that routers aren't the only thing that have to route on the network. There's also a host computer can route information based on its IP address and subnet mask. I know we've talked about those already, but I'll go ahead and start over here with this example. We have two host PCs here, and in some situations they can send traffic directly to each other. And in those situations you would want that to be the case because you don't really need to talk to a router. I've got these connected right here. Now this is typically going to be a switch, but since we're focusing on routing, I haven't really included switches in my diagram. But we've got two IP addresses here, one for PC1, 172.16.1.1. PC2 here's got 172.16.1.2. These are in the same subnet. As you can see, I've got a /24 mask here. For those of you who don't know a whole lot about subnetting, that's 172.16.1.1 through 254. So any IP address in that range is in the same subnet. Since these hosts are in the same subnet, they can communicate directly with each other. They can communicate directly with each other based on source and destination IP address, obviously. That's going to be in their layer 3 encapsulation. But layer 2, they can communicate with each other based on their MAC addresses. So when this guy wants to send a message to him, he uses obviously his source destination address will be 172.16.1.1. His destination will be 172.16.1.2. And then he's going to send an ARP broadcast in order to discover this guy's MAC address. That broadcast, since they are on the same subnet, will be responded by this guy, and it will say, this is my MAC address, and then that's going to be filled out in the layer 2 addressing. So technically, you don't even need to talk to a router here in order for these to pass information between each other. Now, when we talk about routers themselves, things aren't exactly the same. And just at my bullet points here, you get that addressing information there via DHCP, Dynamic Host Configuration Protocol, which a DHCP server will give you potentially a plethora of more information, such as not only your IP address, your subnet mask, your default gateway. Your default gateway will be the router that is on that subnet. Each router is going to have an interface, obviously, that connects to your network. And that interface is going to be its IP address. And that's what's known as a default gateway. So anytime you need to talk to somebody off of your own subnet, in this situation, they communicate directly with each other because they're on the same subnet. If we wanted to communicate with PC3 down here, he's on 172.16.3.3, and this is actually /24. Once again, that's 172.16.3.1 through 254. Since these guys are on the 1 network here, they can communicate directly. Well, let's say PC1 needed to talk to PC3. It needs to go through this router. Not only is it obvious here, but to this computer, it doesn't necessarily know the physical layout of the network. He just has to assume, okay, hey, he's not on my subnet based on my subnet mask. And I know that his destination is this IP address here. Since he's not on my subnet, I have to send that information to this guy here, which is 172.16.1.254. So that's the default gateway. So you can assign, this can be given to you via DHCP, which will give you the default gateway. Obviously, it'll give you DNS, which we'll talk about here in a little bit, or that can be statically assigned. I'm sure most of us have seen before where you go into your Windows desktop and you go to assign an address under TCP/IP settings, and when you click configure automatically, that's when a DHCP server gives you all that information. Otherwise, it's going to be statically configured. So if you uncheck that box, you have to be able to fill out all that information for it to be able to communicate on the network. Like I said earlier, if they're on the same subnet, the host can communicate directly. If they're on different subnets, that's when they have to have a router. So how do routers know where to forward traffic? It's based on a routing table that they build, and it's dynamic. Not always dynamic, but most networks these days are using dynamic routing. You can have that configured with static routing as well. So the differences between a MAC address table and a routing table. Well, first off, we know that switches build MAC address tables. I know we talked about this last week. A switch has an interface plugged into it. If that goes to a host, every time that host sends out information, the switch says, oh hey, there's the source MAC address. I need to put that in my MAC address table, so anytime somebody wants to send something to that person, I know where it came from, and I'll just send it right out that interface. With routers, it's not necessarily the same. Now, I know we talked about router ports. Each port or interface is going to have an IP address associated with it. Now, what it's going to do is it's going to populate this in its IP routing table. It's going to say, I've got this network directly connected to me. So in a sense, it's kind of like a MAC address table in that way, where it knows what's directly connected to it because it's been statically assigned on its interface. But what routing protocols can do and how routers know how to forward traffic, it can be done with routing protocols dynamically. So if we have this router right here, and I need to have PC1 communicate with PC3, what do these routers need to do? They need to be able to communicate with each other and say, this is the network that's attached to me, and I need to be able to know where to forward to that network based on what I have in my routing table. So R2 needs to tell R1, I've got this network right here. And if you want to send anything to this PC3, it's got to be sent to me. Now this diagram here could have another router over here, but you could have another one attached to it, R4. This can get a lot more complex. This is essentially what I'm saying. For it to know what's attached to router 4 here, you can use dynamic routing protocols, which we're going to talk about here in a minute. But I guess what I'm trying to say here is, in order for these computers to be able to communicate with each other, they need to be able to talk to the router, which by using their default gateway, which is assigned via DHCP or statically configured. And then they also need to have a routing table that has information in it telling it how to reach this network. And that segues us into routing versus routed protocols. Routing protocols, we have RIP, IGRP, EIGRP, OSPF, ISIS, and BGP. That's a long list. Routing protocols, and they each act a little bit differently, sometimes more differently than others. So I don't expect you to memorize all these. I know for CCENT it's very important to know about RIP. And we'll dive more into RIP later in another video, but for now, just know that there are a plethora of routing protocols. Routing protocols allow routers to dynamically advertise and learn routes. And they also help determine which routes are available and which are the best. So that communication between routers is done with routing protocols like RIP and IGRP. And these allow you to forward routed protocols. Just a few here listed: IP, IPX, AppleTalk, DECnet. These are just protocols that are transported over network. It's easy to confuse the two when you think routed protocols versus routing protocols. Well, a routed protocol typically has an addressing scheme associated with it. So an IP has an IP address associated with it in order for routers to be able to know how to forward traffic. If we're talking about a switch, we're using a MAC address. We're not even getting to layer 3 yet. Anytime a switch is looking at an address, it's looking at the MAC address at layer 2 to forward things on. But once we start getting to layer 3, we're looking at more of a macro scale here with routers. And then you would need another addressing scheme. Otherwise, they wouldn't be able to communicate with anyone other than people on their own subnet. So, as I talked about earlier. I did mention this earlier. The routing table is going to contain directly connected routes, subnets. So up there, R1 is going to have 172.16.1.0/24. It's going to have every IP address associated with that interface in its routing table. It's not going to have every IP address. It's just going to contain the actual subnet itself. And then they're going to advertise their name through so the routing table for R1 will also have, if it's running RIP, EIGRP routing protocol, it will also have information from R2 down there, 172.16.3.0/24. It'll have that in its routing table based on advertisements and communication between two routers. They can also be statically configured. You could bypass the concept of a dynamic routing protocol by simply statically configuring R1. So you could say, well, R1, I'm in you right now, and I'm going to configure you to say, I know where 172.16.3.0/24 is. It's out that interface. Let's just say this is fast Ethernet 0/1. we'll say, hey, anytime you have anything that's in that subnet, just send it out here. It's one way to get around the idea of a dynamic routing protocol, because in general, they're not the easiest concept to understand. There's a lot to routing protocols. There's a lot of things you need to understand about the communication between routers. So you can statically configure this. There's not a whole lot of flexibility, however. If this route were to go down, let's say this goes down for some reason. Maybe it gets cut. I don't know. And we've got a switch down here, which connects to this host. And that switch connects to R4 and R2. I'm kind of messing my drawing up here. But basically, essentially what I'm saying is R1 has two different routes to get to this host in this network. It can do it via this, straight path here to R2. But if we lose this link here, it's got to be able to go through here. So the flexibility of dynamic routing protocol can allow it to say, oh, hey, I lost that link. I need to have another route in my routing table that directs me this direction so that I can actually send information here. So static routing has its place in a network. But if we're talking about flexibility and dynamic attributes of a protocol, you want to use dynamic routing. And obviously, the routing table itself is going to contain where I need to send information. So if I have a packet destined to R3, the routing table is going to include not only the subnet, but it's going to say where I need to send it in order to reach that subnet. Oh yeah, I have a routing table here just because I figured if we're going to talk about it enough, we may as well put it in here. So you can do the show IP route command in a router, and it'll give you a whole bunch of codes here. And these can be kind of confusing. C is for connected, so it's going to tell you how it learned about this route. You've got connected routes, you've got static routes, so we're going to talk about those too. And we talked about RIP. This is a route learned from RIP. Mobile, I'm not sure exactly what that is, but we've got BGP here, EIGRP, and they go through a list, essentially a list of codes for you to be able to determine how the route was learned. And down here we've got an S next to this subnet here, 192.168.10.0. That means this is statically configured. Somebody went into the router, typed IP route, and gave it that route. Same thing with this here. This O, however, was learned via OSPF. This is one of the dynamic routing protocols we were talking about earlier. C stands for connected. So this is directly connected. Just by looking at this routing table here, we can tell these are directly connected routes. This has been dynamically learned via OSPF, and these have been statically configured. They're not directly connected, but we have a route to them based on what somebody input into the router itself. Onward to DHCP, I did talk about that a little bit earlier. A way to essentially have an IP address assigned to you. It uses a process that I would refer to as DORA. Easy way to learn: discover, offer, request, acknowledge. So you plug in a computer into a network. The first thing it does is say, I need to find a DHCP server to give me an IP address. So it sends out a discover. The DHCP server gets that message and says, hey, I'm a DHCP server. I can give you an IP address. So then the PC itself says, I would like to request an address. Then the server sends back an acknowledgement and says, this is your address, including your subnet mask, your default gateway, your DNS. And speaking of DNS, it's a domain name system. So we go to a browser and type www.yahoo.com. A router doesn't know what that is. It needs to have an IP address associated with that. So what a DNS server does is say, hey, you're trying to reach www.yahoo.com. I'm going to send that information to my DNS server as a computer because I don't know exactly what IP address that is. And then the server says, oh, I know what that is. It's this IP address. And then that allows them to communicate directly over the network. ARP, I know we talked about ARP broadcasts earlier. And a good example of that would be here. When a DHCP server gives you an IP address, a subnet mask, and a default gateway, it gives you the default gateway that is an IP address. If I need to communicate directly with something attached to my subnet, how do I do that? That's all done with layer 2 and MAC addresses. Make sure I'm in frame here. That's all done with MAC addresses. So it needs to know the MAC address for the default gateway. But all it has is an IP address. So what ARP does, Address Resolution Protocol, they'll send out a broadcast and say, hey, or actually it'll send a direct message to 172.16.1.254 and say, hey, what's your MAC address? And this guy will say, this is my MAC address. Okay, well now I can communicate with you because I need to have my layer 2 addressing aligned along with my layer 3 addressing if I need to communicate directly with R1. On to ping. This is a way you can test connectivity in general. It sends in an ICMP echo request. So if I wanted to test and make sure that all my routing and my connectivity and cabling between PC1 and PC3 are good and they can communicate, you can send a ping message. Typically you can do that on command line or the router, you can do that on a computer. And just it'll send an echo request down to PC3 and then the PC3 will send an echo reply. And once you see, it'll give you a time to live. And then once you have received that, you can verify that there is connectivity between those two devices. That's it.